Welcome to Hired in IT. Our mission is simple: help you build the skills that employers actually want. Whether you're trying to land your first IT job, switch careers, earn a promotion, or increase your salary, we're here to help. Every video is thoroughly researched and designed to make complex IT topics easy to understand. If there's an IT topic you'd like us to cover, leave a comment below. We may turn your suggestion into our next video. Turning IT knowledge into career opportunities. 9 p.m. on launch week. The app keeps timing out. Users are refreshing every few seconds, and the AWS bill has quietly doubled. The team launched a compute-optimized instance with 8 vCPUs, thinking more CPU meant faster. It didn't. If you watched part 1, you already know how to launch and secure an EC2 instance. Today the question is, which instance type actually fits the job? Because the wrong one will cost you users and money at the same time. By the end of this video, you'll be able to do 3 things that separate someone guessing from someone who knows EC2. 1. Map any workload to the right one of the 5 EC2 instance categories. 2. Decode a name like C7G.large and know exactly what the C, the 7, the G, and the word large each mean. 3. Avoid the T-series burstable billing trap that quietly charges beginners extra. Those are the payoffs. Let's earn them. Here's the mental model that makes everything else stick. An EC2 instance type is not you handpicking a CPU and RAM. It's a pre-built spec sheet, a fixed combination of virtual CPUs, memory, storage, network bandwidth, and sometimes a hardware accelerator like a GPU. Think of it like ordering a meal combo instead of shopping for every ingredient. When AWS says C7G.large, they've already decided the ratio for you. Your only job is to pick the combo whose strongest ingredient matches what your app actually craves. AWS offers a large and evolving EC2 catalog. To make the catalog useful for beginners, this lesson starts with 5 practical workload categories. General-purpose instances balance compute, memory, and networking. They are often a reasonable first category to investigate for development environments, application servers, and many ordinary business workloads. Compute-optimized instances emphasize CPU performance. They can be appropriate for workloads that profiling shows are CPU-bound. Memory-optimized instances provide large amounts of memory relative to compute. They can be useful for large caches, in-memory databases, analytics, and other memory-heavy workloads. Storage-optimized instances are designed for demanding storage access patterns. Depending on the family, that can mean high local storage capacity, low latency, high throughput, or high random I/O performance. Accelerated computing instances provide specialized hardware such as GPUs, Inferentia, Trainium, FPGAs, or video accelerators for workloads designed to use them. AWS also lists high-performance computing, or HPC, as a distinct category for tightly coupled cluster workloads that need specialized compute and high-speed internode communication. Treat these categories as starting points, not automatic answers. A real workload can need strong CPU, a large cache, high network throughput, durable storage, and a specific processor architecture at the same time. The professional workflow is always the same. Understand the workload, identify the constraints, compare compatible types, test, measure, and review cost. Here's the single most important idea about EC2 instance families. Optimized doesn't mean everything gets better. It means the instance family is designed with a particular workload profile in mind. Think of this chart as showing relative workload emphasis, not a price-performance guarantee. General purpose balances compute, memory, and networking for workloads without one dominant resource requirement. Compute Optimized emphasizes processor performance relative to memory for CPU-intensive workloads. Memory Optimized emphasizes RAM capacity relative to compute for workloads with large active working sets. Storage Optimized emphasizes particular storage characteristics, which may include high throughput, high random I/O performance, low latency, or large amounts of local instance storage, depending on the family. Accelerated computing adds specialized hardware such as GPUs, Inferentia, Trainium, FPGAs, or other accelerators for workloads designed to use them. And HPC-oriented options address another specialized requirement: tightly coupled, distributed workloads where communication between nodes can be critical to performance. So when someone says, just get a bigger instance, ask, bigger in which resource? More CPU won't necessarily solve a memory bottleneck. More RAM won't necessarily solve slow storage. A GPU won't automatically improve software that isn't designed to use it. The family gives you a direction. The workload tells you which direction to investigate. Quick check. You have a small web application with normal traffic. Measurements don't show a major CPU, memory, storage, or accelerator requirement. Which EC2 category would be a reasonable place to start your investigation? Pause if you need to. The answer is general purpose. General purpose instances balance resources instead of emphasizing one particular area. Families such as M and burstable T instances where the CPU pattern fits the burstable model may be candidates to evaluate. But don't turn that into small web server equals T-series. A T-series instance uses a burstable CPU model, so you need to understand the workload's baseline and peak CPU behavior, credit characteristics, and cost. If no resource is clearly dominant, general purpose gives you a reasonable starting hypothesis. Then profile the real workload. Remember, start with a workload category. Then choose the specific family and instance type from evidence. M and T are both general-purpose EC2 families, but they use different CPU performance models. That's the distinction I want you to remember. M family instances provide fixed performance general-purpose capacity. T family instances provide burstable general-purpose CPU performance. A T-series instance has a baseline level of CPU performance and uses CPU credits to burst above that baseline when additional processor capacity is needed. That can make T instances attractive for workloads with relatively low average CPU utilization and occasional bursts. But don't interpret that as T is for temporary servers and M is for always-on servers. A T-series instance can run continuously. The question is whether the application's CPU behavior fits the burstable model economically and operationally. Suppose your application has long periods of low CPU use and occasionally becomes busy. T-series may be worth evaluating. Now, suppose CPU demand is consistently elevated for long periods. Don't automatically assume T-series is still the lowest cost choice. Compare average CPU utilization, peak behavior, the T-series baseline, CPU credit behavior, unlimited mode charges where applicable, and the total cost of an appropriate fixed performance alternative. The distinction isn't steady server versus temporary server. It's fixed CPU performance model versus burstable CPU performance model. And Scene 9 will show you exactly why that matters. Burstable T-Series instances are designed for workloads with a baseline level of CPU use and occasional periods of higher demand. They earn CPU credits while usage stays below the baseline. Those credits can be used to burst above the baseline for a period of time. T3, T3A, and T4G instances commonly use unlimited mode by default. In unlimited mode, an instance can continue using CPU beyond its earned credit balance by spending surplus credits. That can be useful. It avoids an immediate performance cap during an unexpected spike. But it also means sustained average CPU usage above the baseline can create additional charges if the instance cannot earn enough credits over time to repay the surplus credits it spent. Do not diagnose the situation from one metric alone. CPU credit balance shows earned credits available to a burstable instance. CPU surplus credit balance shows surplus credits the instance has spent. CPU surplus credits charged shows surplus credits that have resulted in charges. Use CloudWatch to review CPU utilization alongside these credit metrics. Then compare the workload's average and peak behavior with the cost of a fixed performance instance of an appropriate size. A T-Series instance can be a cost-effective choice for variable workloads. It is not automatically the cheapest choice for sustained CPU-heavy work. The rule is simple. Monitor the application, the CPU pattern, the credit behavior, and the bill together. Let's make compute optimization concrete. Imagine a media processing application that converts uploaded video into several formats. As the workload grows, processing becomes slow. Before changing EC2 families, the team profiles the workload. Memory isn't exhausted. Storage isn't the limiting resource. Network calls aren't causing most of the delay. Instead, CPU utilization remains consistently high while the processing jobs run. Now we have evidence of a CPU-bound workload. That's when compute-optimized instances become a category worth investigating. Compute-optimized families, commonly represented by the C family, provide a CPU-to-memory profile designed for compute-intensive workloads. Potential use cases include batch processing, media processing, scientific and engineering calculations, certain game server workloads, high-performance application servers, and other workloads where processor performance is a major constraint. But remember the methodology. Don't see high CPU once and immediately migrate everything to a C-family instance. Ask, is CPU consistently the bottleneck? Can the application be optimized? Would horizontal scaling help? Does the workload need a different processor architecture? And does the performance improvement justify the cost? Compute optimized isn't the automatic fix for a slow application. It's a strong candidate when measurements show that compute is actually the limiting resource. Before we go deeper, let's pull one from part 1. A company runs an in-memory database that holds its entire dataset in RAM. Which EC2 family should they look at first? If you said memory optimized, you're already applying the bottleneck first mindset. Memory optimized instances, the R and X families, give you a much higher memory to CPU ratio, which is exactly what an in-memory database needs. That's the preview for the next scene. Now let's look at memory-optimized instances. Imagine an analytics or database workload with a large active working set. The application repeatedly needs fast access to a large amount of data. As the workload grows, measurements show increasing memory pressure. The active working set no longer fits comfortably in available RAM, and that memory constraint is contributing to performance problems. Now, memory capacity has become an important infrastructure requirement. That's where memory-optimized instances become a category worth investigating. Families such as R and X are designed with large amounts of memory relative to compute. Potential workloads can include in-memory databases, large caches, memory-intensive analytics, real-time data processing, and other applications with large active working sets. But don't memorize. Database equals memory optimized. A database can be CPU bound, storage bound, memory bound, network bound, or constrained by application design or queries. The same principle applies here as everywhere else in EC2. Measure first. If the evidence shows memory is the constraint, then investigate an instance family designed to provide more of it. A cache can reduce database work by keeping frequently used data close to the application. In one common design, users reach application servers. The application checks a Redis or memcached cache before it queries the database. If the requested data is present in the cache, the application can respond without making the slower database query. Memory capacity is often important because the cache needs room for the working set of hot data. But do not turn that into a rule that says, Redis always belongs on memory optimized. A cache can also become limited by CPU, network throughput, connection count, storage behavior, eviction policy, serialization cost, data model design, or the performance of the backing database. If measurements show that the cache is memory constrained, investigate memory-optimized options. If measurements show high CPU, profile commands, data structures, serialization, and application behavior. If network throughput or connection pressure is limiting performance, investigate the network path and the instance's network capabilities. The family is not the diagnosis. The family is one possible response after you understand the diagnosis. Here's a misconception that can cost teams money. A server is slow, so give it more RAM. Sometimes that works. Sometimes it changes almost nothing. Imagine a compute-heavy application. Monitoring shows that CPU utilization remains extremely high during processing, but the system already has enough available memory for its active working set. If memory isn't the constraint, simply adding more RAM may provide little or no performance improvement. You're increasing a resource the workload wasn't waiting for. The reverse can also happen. If a workload is memory constrained, adding CPU may do very little. If the workload is waiting on storage, increasing CPU and RAM may not address the actual problem. And if most of the delay comes from an external API or database call, resizing the EC2 instance may barely change the user experience. That's why the question isn't, which instance is more powerful? The question is, which resource is limiting this workload? CPU, memory, storage, network, an accelerator, or something outside the EC2 instance entirely? Find the bottleneck first. Then spend money on the resource that actually addresses it. Before we get into storage-optimized instances, quick recall from Part 1. If your data has to survive a stop and start, choose a persistent storage option rather than ephemeral instant store. Pause and answer. The answer is EBS, not instant store. Instant store data is not designed to survive a stop, hibernate, or terminate. That distinction matters because storage-optimized instances lean hard on local instance store, and you need to know when that is safe. Now let's talk about storage-optimized instances. This category is easy to misunderstand because people often reduce storage performance to one phrase: fast disk. But storage performance has multiple dimensions. 3 terms you should understand are IOPS, Throughput. Latency. IOPS means input/output operations per second. It matters when a workload needs to perform large numbers of storage operations. Throughput measures how much data can move over a period of time. That can matter for workloads reading or writing very large amounts of data sequentially. Latency describes how long an individual storage operation takes. A workload can care about one of these, or several, at the same time. Storage-optimized EC2 families are designed for demanding storage access patterns. Depending on the family, that may include large amounts of local instance storage, high IOPS, high throughput, low latency, or a combination of storage characteristics. Potential use cases can include large-scale data processing, distributed file systems, search workloads, data warehouses, log processing, certain databases, and other storage-intensive applications. But here's the critical architecture lesson. Storage optimized does not automatically mean durable storage. Some storage-optimized instances rely heavily on local instance store. Instance store volumes are physically attached to the host and can provide excellent performance for the right workload. But as you learned in the previous checkpoint, instance store data is ephemeral. You should not design around it as though it were persistent EBS storage. If important data is placed on local instance storage, your architecture needs an explicit durability strategy. That might involve replication, rebuilding data from another source, distributed storage, durable backing storage, or another recovery design appropriate to the application. And before changing instance families, investigate the entire storage path. Maybe the bottleneck is the EC2 instance, but it could also be the EBS volume type. Provisioned IOPS, throughput configuration, queue depth, file system behavior, database design, query design, caching, or the application itself. So remember, high IOPS, high throughput, and low latency are related, but they are not the same thing. Measure the storage pattern. Understand the durability requirement. Then determine whether storage-optimized EC2 is actually the right response. Once you know the naming pattern, verify it from the command line. Run the Describe Instance Types command with a filter for the R6G family and project the instance type and its memory size. The wildcard pattern shows every R6G option, from small to 16x large, with a MB value you can compare. This is how pros check current specs instead of memorizing a table that changes. You just listed R6G instances. So tell me, in a name like R6G.large, what does that leading R signal? It is tied to the memory-optimized family, the RAM-focused group, not a compute or storage line. A fraud detection model has to score a transaction in milliseconds. Behind the scenes, that is thousands of matrix operations. Multiply this vector, add this bias, repeat across a huge neural net. A general-purpose CPU has to chew through them in order. A GPU does them in parallel. That is what accelerated computing means. You attach a coprocessor, a GPU, an FPGA, a chip you can reconfigure for custom hardware tasks, or custom silicon. That is specialized for this workload and far faster than a general CPU. Training and inference are different stages of a machine learning workload. Training updates a model by processing large data sets and repeatedly calculating gradients. That can require substantial accelerator memory, throughput, and distributed training capability. Inference runs an already trained model to produce predictions, classifications, recommendations, or generated output. A large GPU instance can be appropriate for some training and inference workloads. But an expensive GPU is not automatically the best way to serve every trained model. For example, AWS P4D and P4D instances are GPU-based options associated with demanding training and high-performance compute workloads. AWS Inferentia-powered instances, including INF2, can be strong options to evaluate for supported deep learning inference workloads. The word evaluate matters. Your model must be compatible with the selected hardware and software stack. For Inferentia, that can involve AWS Neuron support and model compilation. Your decision also depends on latency requirements, throughput, model size, batch size, memory use, operational tooling, engineering effort, and total cost. Some inference workloads may run best on GPUs. Some may run well on INF2. Some may be more economical on CPUs, on another accelerator, or in a managed service rather than a self-managed EC2 instance. Benchmark the actual model and serving path before committing to a long-running fleet. Accelerated computing is not one thing. AWS offers different kinds of specialized hardware for different workloads. P-series instances are GPU-focused and are often evaluated for demanding training, high-performance computing, and GPU-accelerated workloads. G-series instances are commonly associated with graphics, visualization, video, virtual workstations, and some GPU-based machine learning workloads. Inf-series instances use AWS Inferentia for supported deep learning inference workloads. Turin-series instances use AWS Trainium for deep learning training workloads. F2 instances provide FPGA-based acceleration for workloads that can benefit from custom hardware logic. VT1 instances are designed for video transcoding workloads. AWS also offers other specialized families, and the available catalog changes over time. Do not treat this as a permanent complete list or assume that a label makes a workload compatible. The right accelerator depends on the framework, model or application design, drivers, compiler support, operating system, region availability, performance target, and cost model. Use the category to narrow the search. Then test the real workload. Pause for a scenario. A company has already trained a model. Now it needs to serve real-time predictions and wants to reduce cost without missing its latency target. Which family should it investigate first? A strong answer is, investigate inference-oriented options, such as ENF2, if the model and software stack are compatible, then benchmark them against the relevant GPU and CPU alternatives. The answer is not, ENF2 always wins. A production decision needs evidence. Can the model run on the selected hardware? Does the serving software support it? What is the latency at the required throughput? What is the cost per useful prediction? And how much operational work does the platform require? The family gives you a hypothesis. Benchmarking gives you the decision. Let's find current instance information in the AWS tools rather than relying on memory. In the EC2 console, open the launch flow and review the available instance types for your region and AMI architecture. The drop-down is useful for selecting a type, but it is not the whole research workflow. Use AWS's instance type documentation, the EC2 Instance Type Finder, the Instance Comparison Experience where available, and the AWS Pricing Calculator to compare candidates. Start with the workload requirement. Do you need a specific CPU architecture, a minimum memory amount, higher network performance, local instance storage, GPU or other accelerator support? Then narrow to compatible types in the correct region. Finally, compare the exact specifications, vCPUs, memory, network performance, EBS capability, local storage, supported features, operating system compatibility, and current price. The goal is not to find the biggest machine in the dropdown. The goal is to build a short list of compatible candidates and test the one that best matches the workload. When an instance feels slow, start by identifying the limiting resource. If the workload is consistently CPU-bound after you profile the application, investigate compute-optimized options. If measurements show the active working set does not fit in memory, investigate memory-optimized options. If storage performance is limiting the workload, investigate the storage architecture first. That may involve EBS volume type, provisioned IOPS, throughput, database design, caching, file system behavior, network paths, or storage-optimized instances with local storage. If the workload can use GPUs, Inferentia, Trainium, FPGAs, or another accelerator, investigate accelerated computing options and benchmark compatibility. If no resource is clearly dominant, a general-purpose instance can be a reasonable first category to test. The diagram is a decision roadmap, not a prescription pad. A metric points you toward a category. Testing, architecture, and cost analysis determine the final instance type. EC2 instance names contain useful clues, but read them as naming conventions, not as full specifications. In a name such as C7G.large, the leading C identifies the compute-optimized family. The 7 identifies a generation. The G indicates an AWS Graviton-based variant. And large identifies the size tier within that family. Other suffixes can signal useful differences. For example, some N variants are designed with enhanced networking characteristics. Some A variants use AMD processors. Some I variants use Intel processors. Some names include suffixes that indicate local storage or other capabilities. But the same letter does not replace the specification sheet. Before choosing an instance, verify the exact CPU architecture, vCPU count, memory, network performance, EBS performance, local storage, accelerator support, region availability, operating system compatibility, and current price. Use the name to ask better questions. Use the current documentation to get the answer. Instance size labels such as large, X-large, and 2X-large indicate different capacity points within a family. Larger sizes often provide more vCPUs, more memory, and potentially higher network or storage capacity. But do not assume every resource increases in exactly the same ratio across every family and size. The smallest size is not automatically a development machine, and the largest size is not automatically the right enterprise answer. A small instance can be too constrained for a test environment. A large instance can be necessary for a real-time production workload. The label tells you relative position within a family, not business importance. For each candidate, check the exact numbers. How many vCPUs? How much memory? What network capability? What EBS or local storage capability? What processor architecture? What is the price in this region and operating system? Then, model the expected cost, test the workload, and resize based on measured evidence. Capacity labels are a starting point. Specifications and benchmarks make the decision. Naming check. In a name such as C5N X large, what does the N suggest? It suggests that the family variant has enhanced networking characteristics compared with related variants. That does not mean you can skip the specification sheet. The exact network performance, EBS performance, processor, local storage, and supported features depend on the complete instance type and generation. Use the name as a clue. Then verify the full current specification before you design around it. EC2 also gives you another important choice: processor architecture. You may encounter Intel, AMD, and AWS Graviton-based instance types. Intel and AMD use the familiar x86-64 architecture supported by a huge software ecosystem. Graviton uses the ARM architecture and can provide attractive price performance for compatible workloads. But don't choose a processor based only on hourly price. First ask, does my operating system support this architecture? Does my application run on it? Are my libraries and compiled dependencies compatible? Are the container images I use available for this architecture? Does my monitoring, security, or management software support it? Then compare performance. A lower hourly price doesn't automatically mean a lower total cost if the workload takes longer to complete or requires significant engineering effort to migrate. On the other hand, a compatible workload may gain meaningful price-performance benefits from a different processor choice. That's why the correct comparison is broader than Intel versus AMD versus Graviton. Compare compatibility, performance, price performance, migration effort, operational requirements, and total cost. Then benchmark the real application. Processor architecture is another design decision, not just another letter in the instance name. Here's an important professional habit. Don't memorize an EC2 specification table. The EC2 catalog evolves. New generations appear. New processors become available. Pricing varies. And not every instance type is available in every region. Instead, know where to find current information. Start with the EC2 instance types documentation to compare current families and specifications. Use the EC2 instance type finder and comparison tools where available to narrow your candidates based on workload requirements. Then use the AWS pricing calculator to model expected cost before you deploy. But the work doesn't stop after launch. Once supported workloads are running, AWS Compute Optimizer can provide recommendations that may help identify opportunities to right-size resources based on configuration and observed utilization metrics. Treat those recommendations as evidence, not automatic commands. Before resizing a production system, consider peak periods, seasonal behavior, application headroom, failover requirements, deployment behavior, performance objectives, and business growth. The professional workflow is: use current documentation before deployment. Model the cost. Monitor the real workload. Review right-sizing recommendations. Then make a deliberate decision. That's much more reliable than memorizing that one instance type has a certain amount of RAM today. You may also see high-performance computing, or HPC, as a distinct EC2 category. HPC workloads are not simply jobs that use a lot of CPU. They are often tightly coupled distributed workloads, such as scientific simulations, engineering models, computational fluid dynamics, weather modeling, and large numerical calculations. In these systems, many nodes must exchange data quickly and predictably. The network between nodes can be as important as the processors inside each node. AWS HPC-oriented instances may support high-performance networking features such as Elastic Fabric Adapter, or EFA, along with the placement, operating system, scheduler, storage, and cluster design required by the workload. If a workload is a single CPU-bound job, a compute-optimized instance may be the right place to begin. If the workload is a tightly coupled cluster where internode latency and bandwidth determine performance, investigate the HPC category, compatible networking, placement strategy, and cluster architecture. HPC is a specialized design problem. It needs end-to-end benchmarking, not just a high vCPU instance type. Final category checkpoint. A university is running a large scientific simulation across many compute nodes. Each node performs heavy numerical calculations. But measurements show that one of the biggest performance constraints is communication between those nodes. The workload needs high bandwidth, low latency internode communication. Which specialized EC2 category should this make you investigate? High-performance computing, or HPC-oriented options. But don't stop at the category name. For tightly coupled distributed workloads, the network between nodes can be just as important as the processors. You may need to evaluate Elastic Fabric Adapter, or EFA. Placement strategy. Compatible instance types. Cluster topology. Storage architecture. The operating system and scheduler. And the application's communication pattern. Here's the distinction to remember. A single server performing a CPU-intensive job may lead you toward compute optimized. A tightly coupled distributed workload whose performance depends heavily on communication between nodes should make you investigate HPC-oriented architecture and networking. Don't memorize that as an exam shortcut. Understand why the architecture is different. Beginner's guess. Pros diagnose. A beginner grabs the largest instance or the only name they recognize, assumes more vCPUs solves everything, and reacts when the bill lands. A pro names the bottleneck first: CPU, memory, disk I/O, or specialized silicon. Picks a family, chooses a processor, starts small, monitors real usage, then scales. And they run the pricing calculator before anything goes live. Same console, very different bill. Here's the 5-minute workflow you can use whenever someone asks, which EC2 instance should we choose? Step 1. Understand the workload. What does the application actually do? Is it steady or bursty? Interactive or batch? Single node or distributed? Stateful or stateless? Does it have a particular operating system or processor requirement? Step 2. Identify the bottleneck and constraints. CPU, memory, storage, I/O, network, specialized acceleration, durability, latency, availability, compliance, or cost. Step 3. Choose a candidate category: general purpose, compute optimized, memory optimized, storage optimized, accelerated computing, or HPC-oriented architecture where appropriate. Step 4. Verify compatibility. Intel, AMD, Graviton, GPU, Inferentia, Trainium. Make sure the operating system, application, libraries, container images, agents, and tooling support the architecture you select. Step 5. Choose an appropriately sized starting point. Don't automatically pick the smallest instance. And don't automatically over-provision just to be safe. Choose a starting size with the performance and operational headroom the workload actually requires. Consider normal demand, expected peaks, failover behavior, deployment patterns, and growth. Step 6. Estimate cost before launch. Review current pricing. For T-Series, understand the CPU baseline, credit model, and potential surplus credit charges where applicable. Consider storage, networking, public IPv4, accelerators, and other resources, not just the EC2 hourly price. Step 7. Test and monitor. Run the real workload. Watch CPU, memory where you collect it, storage, network, application latency, throughput, error rates, and cost. Then right size from evidence. That's the workflow. Understand, diagnose, narrow, verify, size, estimate, benchmark, monitor, right size. You don't need to memorize hundreds of EC2 instance types. You need a repeatable process for choosing among them. Quick recall from Part 1. Which EC2 feature is commonly used to provide launch time configuration instructions, such as installing an approved agent or configuring a test service when an instance starts? User data. For many Linux AMIs, user data scripts run during the first boot by default. But the exact behavior depends on the AMI, cloud init configuration, launch method, and script format. That is why you test the automation and inspect its logs. Treat user data as a repeatable setup mechanism. Do not place secrets, long-lived credentials, private keys, or sensitive configuration data in it. For production systems, pair user data with version-controlled infrastructure definitions, approved images, IAM roles, secret management services, logging, and change review. Certification questions often describe a workload and ask you to select an architecture or instance category. The key is not to hunt for one magic word. Read the entire scenario. What is the primary performance bottleneck? Does the workload need durable data or temporary local storage? Does it require a specific processor architecture or operating system? Is it a single server, a distributed cluster, or a managed service use case? Are latency, throughput, availability, security, compliance, region availability, or cost constraints included? Then choose the option that satisfies the stated requirements with the least unnecessary complexity. If the scenario says the database is memory constrained, memory optimized may be a strong candidate. If it says the workload needs low latency local data processing and can tolerate ephemeral storage, storage optimized may be relevant. But a professional answer always accounts for all the constraints, not just the first resource word you notice. Here is an exam-style scenario. A workload needs high sequential read and write performance for very large datasets on local storage. The data can be regenerated or is replicated elsewhere. Which category should you investigate first? Storage optimized. The phrases local storage, high throughput, and large data processing point toward a storage optimized category. But do not stop there. You still need to verify the exact durability design, local storage capacity, throughput and IOPS requirements, node count, network behavior, operating system compatibility, region availability, and price. Storage optimized is the starting hypothesis, not the whole architecture. Use this chart as a starting map, not an automatic selector. For a balanced development or application workload, investigate general purpose. For a workload that profiling shows is consistently CPU-bound, investigate compute optimized. For a workload whose active working set is memory constrained, investigate memory optimized. For a workload that needs demanding local storage access and has an explicit durability plan, investigate storage optimized. For a workload that can use specialized hardware, investigate accelerated computing. For a tightly coupled distributed cluster that needs high-speed, low-latency internode communication, investigate HPC options. Then, verify architecture compatibility, exact specifications, workload metrics, availability requirements, and total cost. There are no magic family names. There is a disciplined selection process. 3 skills from this video. First, diagnose before you choose. Identify the workload's real bottleneck and constraints: CPU, memory, storage, network, accelerator compatibility, architecture, durability, availability, and cost. Second, use instance names as clues, not as complete specifications. A name such as C7G large tells you that the type is compute optimized, Generation 7, Graviton-based, and in the large size tier. It does not replace the full instance specification. Third, validate both performance and cost. For burstable T-series instances, review CPU utilization, CPU credit metrics, unlimited mode behavior, and surplus credit charges where relevant. For every candidate, compare current pricing, benchmark the workload, monitor the outcome, and adjust from evidence. That is the difference between picking an instance and designing for a workload. Next, we will separate two decisions that are often confused. One decision is how you pay for compute. Common options include on-demand pricing, savings plans, reserved instances, and spot instances. The other decision is whether you need capacity assurance in a specific availability zone. That is where on-demand capacity reservations come in. These concepts can work together, but they are not interchangeable. Savings plans and reserved instances are primarily discount and commitment constructs. Spot can reduce cost for interruption-tolerant workloads. Capacity reservations reserve matching capacity in a specific availability zone and do not inherently provide a billing discount. In the next video, we will cover when each option fits, how the risks differ, and how to avoid treating a pricing discount as a guarantee that capacity will be available when you need it. Remember, careers aren't built by watching videos. They're built by applying what you learn. Pick one thing from today's lesson, build it, document it, and share it. That's how you get hired. Thanks for watching Hired in IT, where we're turning IT knowledge into career opportunities.